Why is the night sky so dark? The sun isn't up, so you may assume the solution is obvious. But during the day, sunlight scattering off the atmosphere is the only thing giving the sky its blue appearance. Even when the sun is shining, the sky would always be dark if we didn't have an atmosphere, just like on the moon. Therefore, let's reword the query. Why is the cosmos dark? There are many stars in space, each roughly as luminous as the sun. And no matter whatever direction you chose, in an infinite, eternal cosmos, you could always see a star or galaxy if you peered far enough in that direction. Therefore, day or night, the entire sky ought to be as bright as the sun. Does the night sky's darkness, which it isn't, indicate that there is a gap between us and where stars and galaxies simply stop? A line separating something from nothing, a limit to the cosmos? Why is the night sky so dark? Hello everyone, this is AWZ. Welcome to our channel. Don't forget to subscribe. Enjoy. When the sun is at its highest during midday, we are surrounded by a blindingly brilliant light. The light conditions get weaker as the hours go by until nighttime with its absolute blackness finally arrives. But why does space seem to us to be such a dreary thing at night? Considering the countless cosmic light sources that decorate the firmament, the issue of whether or not the night sky should be radiantly bright quickly emerges. Discover why the nighttime view of the stars is always accompanied by a piercing blackness in the next movie, as well as why the universe seems to us to be dark. The Albers enigma. This natural phenomenon gives us on Earth the impression that the sun moves across the sky during the day, and that once it has vanished over the horizon, we are without our primary source of light. The night sky should glow as brilliantly as our sun if the universe is endlessly big and has a uniform distribution of stars. After all, the Milky Way, the galaxy in which we live, is thought to contain up to 400 billion of them. The scientific community would remain enthralled by the big cosmic mystery for decades to come. The Albers paradox refers to the explanations for this issue that Heinrich Wilhelm Olbers introduced to the field. It alludes to cosmological principles that are perfectly followed by world models. This simply means that the observer sees the universe in the same way regardless of his own vantage point or direction of observation. This implies that a universe that is endlessly large and extends in all directions must have a uniform distribution of stars. No matter which way a star shone, its light had to eventually reach the Earth. As a result, the night sky would need to be as luminous as a star's surface. We are proven by a nightly view of the firmament. He ultimately reached the conclusion during his studies that the gases between stars absorb the light that is released. In this sense, the endlessly vast universe idea might likewise be used to solve the light conundrum in space. But as we now understand, the astronomer erred significantly. The gas would heat up and eventually start to shine brightly if starlight shone on it. In actuality, many astronomers in the past held the unshakable belief that the Milky Way would resemble an island universe. This would imply that the universe beyond our solar system is nothing more than an endless emptiness. It wasn't until the turn of the 20th century that this widely held fundamental supposition was proven incorrect. At that time, astronomers realized that the structures in the firmament that were thought to be nebulae were actually far-off galaxies rather than gas clouds. As a result, the area beyond our own bar spiral galaxy is by no means empty. The reason the universe seems so black to us during the night must also have a solution. Contrary to what was formerly believed, the distribution of stars inside space is not uniform. In particular, the glittering celestial objects gather in galaxies, which in turn give rise to massive clusters of galaxies. When applied over vast distances, the fundamental cosmological principle is true. When our eyes stray to the firmament, we are constantly viewing the surface of a star in the boundless cosmos. Does this imply that someday in the far future, terrestrial night will be accompanied by a brilliant brightness? That is not the situation. The universe's stars would have long since dissipated by the time we arrive at that galactic moment in time where we could examine a suitably vast portion of the cosmos. Stars are finite objects, just like all the other celestial bodies that adorn space. In actuality, the dazzling item's nuclear reaction only lasts for a brief period of time. The night sky is not as dark as it seems to our earthly eye, at least not in all spectral regions. In reality, a uniform weak radiation with a maximum wavelength of roughly 1 millimeter or 4/100ths of an inch bombards the Earth from all sides, falling into the microwave region. This background radiation is an evidence of the Big Bang, a phenomenon that is important to ongoing research and which may be demonstrated today. The universe's temperature dropped to around 5,400 degrees Fahrenheit. As a result, stable hydrogen atoms might be created by protons and electrons. In other words, at that moment, the cosmos opened up to electromagnetic radiation. Because the universe is continually expanding, those light particles that were produced at that time are still visible to us today as cosmic microwave background radiation. However, a significant portion of the original potency of this primordial radiation was lost. Cosmic background radiation is only 1/billionth as intense as it once was. In essence, according to the most recent forecasts, this percentage is only 4.9%. Dark energy and dark matter are present in 68.3% and 26.8% respectively, but their presence has not yet been demonstrated empirically. The motions of visible matter can be categorized with the aid of dark matter. But in addition to reducing the cosmic background radiation's brightness, the still rapid expansion of the universe also causes another phenomenon that makes the night sky appear to us to be very dark. The Big Bang occurred approximately 13.8 billion years ago, as was already stated. The cosmos started to expand after this occurrence, in which matter, space, and time emerged from an original singularity. The expansion process is still going strong today. All structures in the cosmos migrate farther and farther away from their original points, to put it simply. This also implies that the gaps in distance between the various cosmic structures are always growing. As a result, this also applies to the innumerable stars as they travel farther and farther away from each other, literally scattering the dark spaces between these collections of celestial objects. They also grow bigger and bigger. Lord Rayleigh, an English scientist, contributed some explanation in the 1870s. We must understand two things about how we experience light, though, in order to fully grasp his argument. First off, the sun emits all visible light colors, from shortwave violet to blue, green, yellow, orange, and long-wave red, though not all in equal amounts. Blue dominates the visible spectrum as a whole. Second, blue light is rather well seen by our eyes, which are better at detecting green light than the other colors. All the hues of visible light together appear to us as white. Consider a cork that is at ease on a still body of water. The cork then moves up and down as a result of waves that are created when a stone is thrown into the pond. The cork takes wave energy and then oscillates up and down. Light waves can also interact with air molecules in a similar way. The energy from the light waves that strike the air particles, however, is promptly re-radiated in a variety of ways. As a result, the original light, which was coming from one direction, is now scattered, re-radiated, in all directions. The size of the molecules or particles and the wavelength of the input light both affect scattering. The fourth power of 1 divided by the wavelength is the scattering formula. The short waves of sunlight, blue, are more effectively scattered by our atmosphere than the long waves of sunlight, red. According to Rayleigh's results, blue light has a roughly 9-fold higher likelihood of scattering than red light because it has a wavelength that is approximately 1.7 times bigger than red light's, 700 nanometers, 400 nanometers. During the day, the sky is filled with this strewn blue light that travels in all directions via the atmosphere. However, compared to when the sun is overhead, sunlight must travel through a greater layer of atmosphere when it is close to the horizon. The majority of the blue light is scattered out as it travels farther through the atmosphere, leaving the light that is left with a proportionately higher orange content. This produces the stunning sunrises and sunsets that we are frequently fortunate to witness. However, these scattering effects vary throughout time. The impact of water vapor, dust particles, ozone, chemical contaminants, and ocular reaction are disregarded in Lord Rayleigh's explanation. A sunrise or sunset's beauty or color can be enhanced or diminished by all of these causes. There is no atmosphere to disperse light in outer space or on the moon. The sun's light does not disperse and moves in a straight line, keeping all the colors together. As a result, when we face the sun, we see a brilliant white light, as opposed to when we face away, where we would only see the void of darkness. We perceive no light, and the sky appears to be dark because there is almost nothing in space to scatter or re-radiate the light to our eyes. This is all for today. Don't forget to like the video and subscribe our channel. Stay tuned with AWZ.